here we are at the end of this chapter. Call this up for you. So this section covers the variety of different membranes, membrane types, and tissue repair. So the three main types of membranes, and when we use membrane in this chapter, I know we use membrane for plasma membrane and other phospholipid bilayer membranes inside cells. And in that chapter, we use the word membrane to refer to a phospholipid bilayer. In this context, the membrane is a sheet of epithelial tissue. So I apologize for no, I didn't do it. I don't have to apologize for that. I understand that it's confusing, so that's why I'm trying to point that out for you. So three basic types: cutaneous, mucous, and serous, or mucosal or serosal. Of these three, the cutaneous membrane, that's just skin. And the mucous membranes are open to the outside world. Serous membranes are contained inside a body cavity completely. That's really pretty much enough for that right now, but we'll go into a little more detail. So cutaneous membrane skin is made up of stratified squamous epithelium that is keratinized. So that means it's multi-layered, stratified, that the cells at the apical layer are the flattened type, squamous, and that these cells have the tough molecule keratin in them to make it waterproof, keep the water on the inside of the body, and also for protection. And it's dry. The other membranes are wet with mucus. A mucosal membrane indicates location. Like I mentioned, it's open to the outside world. The digestive tract, open on both ends. The respiratory tract and the urogenital tracts are all mucous membranes. They are bathed by secretions, or in the case of the urogenital tract, urine. Entire lining of the respiratory tract and digestive tract considered mucosal membranes. Now, a substance is not really considered to have entered the body unless it crosses one of these mucous membranes. Like in the lungs, even though the oxygen is down in the alveolar sacs of the lungs, it's not considered to have actually entered the body until it diffuses into the blood. Same thing with the digestive system. The molecules are broken down into smaller parts, and then they're not considered that they've crossed into the body until they've been absorbed. And undigested wastes, of course, are eliminated from the body at the other end of the digestive tract. Serosal membranes, those are found enclosed in the body cavities. Also, simple squamous epithelium. And many, we've talked a little bit about some of these already. The visceral serosa covers the internal organs. Talked about that in reference to the pericardial sacs and the pleural membranes of the lungs, or each one of those had a visceral membrane that was close to the organ, covered the organ itself, and then it had a little space, and then there was a parietal membrane on the outside of it, and in between those layers, that space is filled with a slippery fluid, similar to mucus. I guess if we found it in outside, we'd call it mucus. So here's an example of that. You can't really tell much, but these membranes line the cavities of the internal thoracic and abdominal cavities, and some of them are special, like the pericardium and the pleural membranes. So let's take a brief moment to talk about repair. When the body's barriers are compromised, when there's an injury, both the inflammatory and immune responses are activated, and then just like any other breach in a safety barrier, we want to get repair started as quickly as possible. So repair can happen in two ways. Regeneration means we just make more of the same tissue that was injured. And in that case, then whatever the original function is restored, and that tissue will just go back to acting just like it was eventually. This would happen, say, in a break of a bone. It was replaced with bone tissue that works just as well, if not better, than the original bone. Fibrosis is where connective tissue replaces destroyed tissue. That would be collagen fibers, and the original tissue is replaced with collagen fibers, and they're not the same as the original tissue, so the function is lost. Let's take a look at a couple of steps. First thing, the inflammation stage sets in, the release of inflammatory chemicals. So those are going to be released by mast cells. Remember, the mast cells have those granules in them with the signal molecules, usually things like histamines, that signal that there's an issue and begin the inflammation process and call out the troops of the immune system. So the first thing that happens is the blood vessels dilate. We'll learn more about this in A&P too. So this dilation of the blood vessels increases blood vessel permeability. We're talking about the smallest blood vessels here, the capillaries. There's small spaces between the cells and the capillaries, and so when the blood vessel dilates, it becomes more permeable. The holes get bigger, and so that means plasma can leak into the injured tissue. Well, everything that's in the plasma is what we're going to need. Everything we need to repair is found in the plasma, so this is going to make it easier. And if a blood vessel is cut, then the clotting process begins. So in this instance, here we have somebody got a boo-boo. They've got a cut that goes all the way down into the dermal layer of the skin, and so it fills with blood, and then clots, and then a scab gets formed over the top. And we've all been through this. You know this already. Then what happens is in the dermal layer, which is mostly connective tissue, there are these mast cells that release these chemicals. So these mast cells get injured, releasing their chemicals, and now this acts as a smoke trail. Imagine that here's the scene of the injury, and that's where the fire is, and then this is the smoke from the fire going out in pretty much all directions, that the white blood cells, neutrophils, and macrophages can come and literally squeeze themselves out between the little cracks in the blood vessel and work their way upstream. They follow the concentration gradient, going in increasing concentrations, just like you would if you saw smoke. You know this, where there's smoke, there is fire. And if you wanted to find out where the fire was, you just follow the smoke. Well, this is just like you follow the trail of chemicals. And there's words for all this, diapedesis and positive chemotaxis. You learn more about those words in A&P 2. So now the white blood cells that are going to come, they're going to phagocytize whatever happens to be there that doesn't belong there. So the blood clot starts to be replaced by granulation tissue. So this is where the actual clotted blood is going to be phagocytized by macrophages. Remember, our macrophages are our cleanup crew. The epithelial tissue begins to regenerate. That would be the epidermis. And the fibroblasts then, we know what those do. We talked about that already. Produce these collagen fibers to bridge the gap in where the injury was. And any debris, so that's dead cells, pieces of stuff that might be in the wound, bacteria, are going to be phagocytized by macrophages. So here we see the collagen fibers breaching the gap. We see the fibroblast hard at work, white blood cells cleaning up. The size of the blood clot is being reduced, and a new blood vessel is coming in to serve the area that was damaged. And then we effect the permanent repair. The scab detaches. That just hurts because Why does that hurt almost as bad as the original injury when the scab comes off, right? That's happened to all of us too. The epithelium thickens, begins to resemble its adjacent tissue. It's regenerating the epithelial tissue. And so what happens is the fibers that are left in the lower layer become scar tissue. And the epithelial tissue above regenerates, goes right back to normal. So eventually these fibers up here will be replaced, but the fibers down here might leave a mark, as they say, make a scar. We probably all have at least one scar somewhere. I have several. And then we're healed, and we're good to go, and we're back to normal. So that's the mostly regeneration with a little bit of scar tissue. Tissues that regenerate extremely well are epithelial tissues, bone, as I mentioned earlier, areolar connective tissue. It's not very complicated, easy to make that. Dense irregular connective tissue, which is mostly just collagen fibers anyway, and blood forming tissue that's also in the bone marrow. So smooth muscle and dense regular connective tissue, moderate regenerating capacity. So the dense regular connective tissue, that's the ligaments and tendons, and those are going to, if they're strained, stretched, or partially torn, they may heal. If it's grade 3 and it's completely ruptured, then that's going to require surgical intervention to fix. It's the torn ends are not going to grow back together. Tissues with virtually no functional regenerative capacity, cardiac muscle cells, and nervous tissue in the brain and spinal cord. So that's an issue because cardiac muscle, if it gets injured and doesn't regenerate, gets replaced by fibrous tissue, then that's not going to be contractile, and that might, depending on where it is, impair heart function. And certainly, we know that brain injuries heal slowly, and spinal cord injuries don't heal at all. Now, here we go. New research shows that cell division does occur. See, now what I always learned is that cardiac muscles and neurons in the central nervous system are amitotic, that they don't divide. But new research shows, and don't often get to talk about the scientific method, but that's how it works. You come out with something and you say, this is what we observed, this is what we think about this is how we interpret this, and you roll with that until you find out that something's different, and that's not how it is. And then you just say, okay, well, new evidence shows that we were wrong on the other bit, and then look what we found now. We see the scientific method going on right now before us as this pandemic unfolds, it being August 1st of 2020, in case you're watching this in the future, and I'm talking to you from the past. When this virus first hit, we didn't know much about it. We didn't know who it affected, how transmissible it was, how fatal it was, and that's what caused all the mayhem, was not knowing. As of now, we know that basically children, young adults are not very vulnerable to this virus. And if you pay any attention to the debacle about masks, at first they said, don't wear masks. If you're not in healthcare, you don't need a mask. And then now you have to wear a mask everywhere you go. So that's how science works. You replace old evidence with new evidence, with old interpretations. You revisit those in context of new information. Now, new research shows that cell division does occur in these tissue types, but not enough to really heal an injury. So efforts are underway to coax them to regenerate better. And this is also an area of research for stem cells. A stem cell can go on to become a variety of different cell types. It's just a matter of nudging them in the direction that we want them to go. And so if we can increase the mitotic rate of these types of cells, or potentially use stem cells to replace that type of cell, instead of forming scar tissue and not being able to regenerate these very important tissues, necessary for life, it's possible, instead of the fibrous repair, that we can regenerate and regain function, and that would be awesome. Because scar tissue that forms in organs, particularly the heart, can severely impact the function. Because what? Well, maybe it can't get as much volume, it can't pump as much blood. Um, could block movement of substances moving through an organ because it's not able to push it through, or open wide enough to let it through. And particularly with the heart, the fibrous tissue that replaces damaged or dead cardiac muscle cells is not going to be contractile, and so that's going to impair um, heart function. And of course, if it's a nerve, well, then that's done. It's not at the moment, then that nerve is no longer going to work as of today. So, one of the issues that you'll find for those of you interested in going into physical therapy, and for those of you who aren't, you know that physical therapists are referred to as PTs, and you think it stands for physical therapist, but in reality, what it stands for is personal torturer, because they make you do things that you don't want to do. You don't want to do them because it hurts, and particularly with some surgeries, joint reconstruction surgeries, you have to get the joint moving as soon as possible to avoid the formation of scar tissue. When I had my last knee surgery, the physical therapist was helping me. He like literally pushing. It was on my knee, and I think I said that. And then they wanted me to straighten my leg out all the way. Well, I hadn't been able to straighten my leg out for months, and I didn't want to because it hurt, and I was afraid it was going to hurt. And the physical therapist said, "Look, if you don't do it now, you may never be able to straighten your leg out again." So I was like, "Oh, okay." And I suffered through it, and now I can straighten my leg out. So um, because the scar tissue, had it been allowed to develop, would stick to neighboring structures and prevent normal functions, meaning range of motion. So we didn't want that. Scarring can potentially cause progressive failure of the organ, particularly the heart, for all the explained reasons that the scar tissue is not contractile. And there is the end of that chapter. Arrivederci. Adios. Au revoir.